Now, Ampere's law, it turns out, is one of the key laws that make up our understanding of how electromagnetism actually works. And the math with Ampere's law can get pretty complicated, but of course, for our purposes in this course, we're going to try and keep it as simple as possible, which is to say, to make it no more difficult than it really needs to be. So just a quick recap. We've talked about how both electric fields and gravitational fields have this inverse square proportionality. So that mathematically, for example, if we look at the electric field, it has a field strength that's related to a constant times the charge at the center divided by the distance squared. So that's fine. And you might wonder, so if we have this inverse square proportionality for electric fields and for gravitational fields, then what should the field strength for a magnetic field do? Because after all, this almost seems like everything should be this way, right? So one thing to keep in mind, though, before we start this or one thing to remind you of, is that magnetic fields are a little different because they often have different geometries. And that's largely because you can't just have magnets always come with dipoles, right? You always have a north-south relationship. So that's something that's going to be a little bit interesting. So let's look, first of all, let's look at the current carrying wire. And one of the things that we talked about was that Ørsted's discovery was that if you have a current carrying wire, the wire actually produces a magnetic field around it. So this again goes with the right-hand rule, right? The right-hand rule, where in this case, what we normally do is we put our thumb in the direction of the current and our fingers curl around the conductor, curl around the wire, right? This was my brush example from the other day. Curl around the wire, and so that's going to be the direction of our magnetic field, okay? So again, we can represent this two ways. We can kind of, in the first example here, we've just drawn the magnetic field as this dot and cross, showing that the magnetic field is out of the page on the left-hand side and into the page on the right-hand side. Or we can try and do this kind of hybrid 3D sketch where we actually show the full magnetic field lines. So what we're curious about here is, the way that we draw these field lines is that they seem to be more and more separated, or at least that's the way the artist has drawn them here. So mathematically, we're curious, or I'm curious, maybe you're curious, about what's the relationship between the distance away from the wire and the field strength of the resultant magnetic field. So that's basically our question. And to answer that question, we're going to have to look at Ampere's law. And so Ampere's law is quite complicated, or at least it looks complicated. And indeed, the math can be quite complicated. For those of you who end up going on further into physics or engineering, you'll probably see Ampere's law and it'll look kind of scary, but it's actually not so bad. So here's the deal. Along any closed path through a magnetic field, the sum of the products of the scalar component of B parallel to the path segment with the length of the segment is directly proportional to the net electric current passing through the area enclosed by the path. Wow, so clear, right? Like, gosh, I'm so glad that that Britta actually wrote this down. Okay, so what the heck are we talking about here? All right, so this little diagram here, this strange looking diagram on the left-hand side, again, that orange cylinder, that's my conductor, okay? And so you can see that the current is pointing along the conductor. And then that weird gray blob around it, that's the closed path that they're talking about in this case. The closed path. So basically you can draw any, as long as you can choose the path, however, whatever geometry you wish, but you need to draw it as a closed path. In other words, you have to come back to where you started. And then as you drive along that path, so driving along that path, that's the delta L, where you have some small length of the path. You're then going to do a calculation of the magnetic field, which is parallel to the path segment. So in the diagram, you can see that I have the magnetic field B, but in this case, what's showing there is that we're only looking at the parallel component of the magnetic field, right? Parallel with the path at that. So at that one little point there, at that one little point of that path, we're just going to be multiplying that B parallel, excuse me, with the delta L. And then what we're going to do is we're just going to go around the whole weird looking shape there and do that whole thing for essentially smaller and smaller values of delta L. The smaller values of delta L that we use, the better our answer will be. Okay. Now so in this equation, this is Ampere's law here, the equation that you see. It's a little scary looking, but it's not actually. The idea is that on the left-hand side, that large E-looking thing is actually a Greek letter sigma, and it means that it's a summation. So it means that we have to add up a bunch of products. The products in this case being B parallel by delta L. So we're always going to be multiplying those two things together, little by little by little, and then adding them all up. And if we do that, then that will equal the right-hand side, which is a strange symbol, mu naught, or mu zero, multiplied by I, which is the current through the conductor. Okay, so this is Ampere's law. Now, one thing that's a little bit, I said about the math that's a bit challenging about this, is that if we have a truly strange-looking path, then this summation, like if we have something that's of the shape that I've drawn, then this summation is really difficult, right? I mean, how are you going to get out your ruler and measure these things? It's going to be very challenging. So in practical circumstances, we don't have to worry too much about this, how this thing is kind of scary looking. We're always going to choose geometries that will allow us to actually do this calculation easily, okay? So this is kind of one of those, I guess not really secrets about physics. It's like we want to make our lives easy as much as possible, even though the reality could be more complicated. So that mu zero symbol there on the right-hand side, that's actually known as the permeability of free space, and it has a special value. So it's just like a regular constant, similar to the K in Coulomb's law, for example. But in this case, it's equal to 4 pi times 10 to the negative 7 Tesla meters per ampere. Okay, so meter, of course, is the unit of distance. Ampere is the unit of current. Tesla is the unit of magnetic field. Okay, magnetic field strength. So that's basically what we're doing there. And the units, although it looks like a bit of a mismatch, that's just to make sure that we get Teslas at the end when we're calculating our magnetic field, because magnetic field is measured in Tesla. Okay, so let's apply this again to some convenient geometry. So we're typically going to use things like a circle or a line. In this case, I'm going to go back to my example of the current carrying conductor, right? And again, the idea is I want to know what the magnetic field strength is at some distance away from the conductor. And the way it was drawn in the previous picture, we have these in circles. So this is the idea. So we're some distance r away from the conductor, and we're looking in some sort of a circular geometry, right? We're just basically going to trace around that path, that circular path. And so we're going to apply Ampere's law. Now again, this looks scary, but it's actually not, because the magnetic field at this point, because we're always on that same circle, that same blue circle, the magnetic field is actually always just the same. Okay, because after all, if you have a circle, the magnetic field is going to be always parallel. The full magnetic field will always be parallel to the circle, right? Kind of like tangent to the circle in some respects. So that's why as we go to the second line, that whole B parallel just becomes B. And then for each little bit of the circle, well, that's fine and all. I mean, we can multiply that out, but really we can just see that, oh, wait a minute, we're just traveling around the circle. And how far do we travel around the circle? That's 2 pi r. That's the circumference of a circle. So that whole nasty nonsense turns into something actually quite simple, quite elegant, right? Which is just B times 2 pi r. That's it. The magnetic field strength times the circumference of a circle. And the right-hand side stays the same. So now at this point, it becomes very straightforward to calculate the magnetic field just with this simple equation. Okay, so oh dear, that's unfortunate, but that's okay. Let's try this as a problem. What is the magnitude of the magnetic field 2 centimeters from a long straight conductor with a current of 2.5 amps? Okay, this is kind of a plug and chug style problem. So, without giving too much away, this is basically what you're going to be working with. So the reason why I pose this problem is I want you to think about this. It's like if we had a little compass, right? One of those little compasses that you sometimes see in the lab, or like on a survival kit or something, like little tiny one. Those don't take those can detect the Earth's magnetic field strength, or the Earth's magnetic field, and but if we had a current carried conductor nearby to them, could we actually deflect them? So in other words, I guess the question I'm asking is this conductor in the question, does it generate a strong enough magnetic field that it could actually deflect a compass needle? Maybe. So let's see. Do the calculation. See what you get. I'll wait.
2,000 years later.
All right. I hope you came back and you plugged in the numbers. So here's what I did. So again, my mu0 is that strange looking thing. The current is 2.5 amps. Don't forget that when you put in your radius to convert it to meters, because you need those units to match, and you get a value of 2.5 times 10 to the negative 5 Tesla. So I put the Earth's magnetic field, the magnitude of the Earth's magnetic. Now, to be fair, the Earth's magnetic field actually varies quite a bit depending on where you are on Earth, but I just took kind of the average value, which is about 40 microtesla, so that you could compare them. So you can see that in this case, the current would actually have a magnetic field less than the Earth's magnetic field. However, they're on the same order. They're very similar. So you could expect that a compass needle would be deflected somewhat by this conductor. Okay. All right. So here's an application for you, for anyone who's perhaps interested in video or other kinds of cable type applications. Coaxial cable. So I used to have to make these things some years ago in my previous job. I actually had these like long spools of coaxial cable, and I had to cut them and attach a connector on the end. And I had this. It was an ordeal. Not really. I mean, but I had to make these things, and so it's important to construct them properly, because if you don't, then the signals that you get out of your electronics, right, the thing that you're trying to measure, will actually have noise in it. So the whole idea of a coaxial cable, it's constructed in such a way so that there is as little noise in the electronic signal as possible. So how do they do that? Well, there's a couple ways. This is kind of the exploded diagram of a coaxial cable. So you can see that the inside, in kind of goldish color, is the inner conductor. So this is basically a couple millimeters in diameter, and it goes just down the middle of the cable. And then surrounding that is something called a dielectric insulator. And then surrounding that is a braided wire shield. So that's kind of the secret sauce. Really, those three layers are there, and you'll see in a second how this kind of works. But those three layers basically are, believe it or not, in kind of parallel plate arrangement, except that we've wrapped it around itself, kind of, sort of. So keep this picture in mind. The outer insulator is just there to make sure that there's no, like, well, I don't know, extra noise, I suppose. I mean, it's a cable. You always want to have some kind of shielding around the cable, just for safety, if no other reason. Yeah. So basically, this is one of these applications. And again, if we can apply Ampere's law to this thing, then we could actually work out, well, what would the magnetic field be? What do you think? Where might we want to care about the magnetic field being generated? Like I said, I used to have to make these things, and the whole reason why I had to make them is because I was making quite sensitive measurements on a very fast time scale, and any kind of noise in those measurements meant that my measurements could be actually wrong, or at least bad. So it was really important that we use these coaxial cables to keep the noise in the signal, or keep the signal as clean as possible. So one thing that we use one of the reasons why you use coaxial cables is because it actually has a really nice property in terms of the magnetic field. After all, the idea is I had like many of these cables coming out of a device, and so they would be quite close to each other. So you could imagine that if one coaxial cable was next to another, and they each had electronic signals, if they were in close proximity, if they had a large magnetic field, they could actually start making noise in one cable. One cable could make noise into the next. So that was part of the reason why we used coaxial cables as opposed to just like regular old single conductor cables or something like that. So have a think about it. Like why would we do this? Why are coaxial cables made with an interconductor and then a dielectric? Dielectric basically just means an insulator, okay? And then another conductor, right? The shield, the braided wire shield, is another conductor. So you have a conductor on the inside surrounded by an insulator surrounded by another conductor, right? That's basically the important part. And then of course you have just the plastic shield that goes around it, the outer insulator, I suppose. Okay, so what do you think? What do you think the magnetic field might be outside of this cable? All right, so let's talk a little bit about a solenoid. So I think for those of you who took grade 11 with me, I may have mentioned at one point that the magnetic field for a solenoid goes kind of like this. So grade 11 was actually the first time that we were introduced to this mu0 number. And if I didn't give you the equation, at least I talked about how the magnetic field is related to the current through the solenoid, as well as N, which it turns out is the number of coils in the solenoid, or at least number of coils per unit length, technically. So if I never gave you the equation, then that's okay. I just perhaps didn't want to get into what this whole mu0 was all about. But you've probably seen this before, although it may have been a while. So here's a cross section of a solenoid. So just so that we're clear, in this case, the X's and dots represent the coil of wire, right? The conductor. So that conductor, right, is going in a coil fashion, and so the dot just means that the current is coming out of the paper, and the X means that the current is going into the paper. Now, if you apply your right-hand rule, I'm going to try and do this here. So let's see. If I'm looking at it, again, you'll have to do it yourself. So I'm going to put my fingers into the paper and then out of the paper. So this means that the magnetic field would be pointing this way, right, according to how my thumb should go. And that's why it shows in the diagram, right? Those arrows there are showing the direction of the magnetic field down the middle of the solenoid. Outside the solenoid, you can see the way it's been drawn here is that we have these loops, right? The magnetic field lines are technically supposed to be loops. But the idea is that outside of the solenoid, we want those magnetic field lines to be as small as possible. And in a perfect solenoid, they're actually 0, but there is no such thing as a perfect solenoid. So the idea is to keep the magnetic field very large down the middle of the solenoid and very small outside of the solenoid. So what we're going to do here is we're going to apply Ampere's law. Now, if you look at this little rectangle that's been drawn with the label ABCD, then what we're going to do is you can see that there are 4 paths in this case: AB, BC, CD, and DA. And for each of those paths, right, so each of those 4 paths, we have to basically calculate what is the product of the parallel magnetic field with the length corresponding to AB, BC, etc. Okay, well, let's look at this. AB is outside of the solenoid. And like I just said, we basically are assumed to have no magnetic field outside of the solenoid. So for that first length, AB, the parallel magnetic field is 0. So boom, done. Similarly, for BC, there is a magnetic field there, but it's not pointing parallel. It's not pointing parallel to CB. It's pointing perpendicular to CB. So therefore, we can say that's 0 also. And same thing with DA. So the only length that actually matters in this case is CD, the length that's drawn basically down the middle of the solenoid. That length has a length of L. So all we're going to do here, in order to apply Ampere's law, is multiply the magnetic field, which is whatever it is, we're probably going to call it B, and multiply that by the length L. Pretty straightforward. Okay. Now that might seem kind of strange because after all, we kind of drew the box in any kind of arbitrary way. Why couldn't we have a larger box? Why couldn't we have a smaller box? It turns out not to actually matter, because when we actually isolate for the magnetic field, then we have this relationship of N over L, where N is the number of coils and L is the length of the box that we've drawn. So the way that this usually gets reported is actually, we just fold those two together. N divided by L becomes little n, which is the number of, it's the turns or coils per unit length, okay? So in that case, it doesn't actually matter what's the absolute number of coils or what's the absolute length of the solenoid. Actually, all we care about is what's the ratio of the two. And that's how we build that one. Okay, so let's try this. What is the magnitude of the magnetic field in the core of a solenoid 5 centimeters long with 300 turns and a current of 8 amps? Give her a try.
1 eternity later.
Okay, so hopefully you got an answer. And if we plug in the numbers, again, using the correct units, we go, at least when I did it, I hope I did this right, you get a magnetic field of 6 times 10 to the negative 2 Tesla, or about 60 millitesla, which doesn't sound like a lot, but if you remember back to the Earth was about 40 microtesla. So this would be a magnetic field strength about 1,000, roughly speaking, 1,000 times larger than the Earth's magnetic field. So if you were to put that little compass next to this magnet, wow, there would certainly be a deflection in that case, right? This is much stronger than the Earth's magnetic field at the surface of the Earth. All right, here are some questions for you to try, folks. They mostly follow along what I've talked about today. So just give those a try and then catch you again in the next video. See ya.